Hello, my name is Jacob Farley, and this is Lab 5 on collisions. So the purpose of this lab is to use data from a self-constructed experiment and tracker to observe and quantify changes in energy in a collision to see the elasticity of the carts. I'll quantify it through a calculated coefficient of restitution. So here we have the equations that we'll need for the coefficient of restitution, um, velocity update formulas for the collision, and just the basic equation for velocity. This is all of my tracker data and the setup picture to give you a better idea of what's going on. This is the first cart that is moving into the second cart. So this is mass A and this is mass B, as described in tracker. Mass A moves at a near constant velocity until a point where it makes contact with cart B, and its velocity decreases significantly. The opposite is true for mass B, where it has zero velocity until cart A makes contact with it, and it increases in velocity rapidly. And the tables for both of these will indicate the exact same thing as the graphs. So we observed mass A to have an initial velocity of 1.44 meters per second using the velocity equations, and to have a velocity of 0.24 meters per second after the collision, and mass B started with zero velocity and ended with 1.02 meters per second. With these values, we can calculate the coefficient of restitution, which comes out to be 0.541. So because it's near 0.5, the collision is moderately inelastic, and that means that there was energy lost in the collision. So I wanted to calculate the total velocity lost. Because it is not perfectly inelastic, we cannot use the inelastic equation in order to set this up. So I had to use the elastic equation. So the elastic equation is set up right there for you to see. And so because the mass of cart A and cart B are the same, you can cancel them out and you end up with the equation 1.44 meters per second equals 1.28 meters per second. So obviously it's untrue because those are not the same. And the energy we lost in the collision can be attributed to three or really two different things: friction and heat, which are essentially the same thing, and noise. If the carts were different masses, the equations we used would be the same, but I would need to know the masses of the two carts in the equation. The way we calculate the coefficient of restitution is still identical because the collision equations account for the differences in mass via the conservation of momentum principle. The only way for the coefficient to be greater than 1 is the object to be moving faster after the collision than before. The only way for that to occur is for a system to experience a net energy gain, kinetic energy gain, or for it to have a force acting on it. An example would be if the carts were positioned on a downhill track instead of a level one. The carts would accelerate due to gravity as well as the collision, and the final velocities would definitely be faster than the initial, giving a positive coefficient of restitution. Although the findings and numbers are very consistent with what they should look like conceptually, there could be minor changes in numbers between this experiment and a perfectly orchestrated one. If there was a slight slant in the track the carts were moving on, the answers would be impacted. The only other unaccounted for source of error is human error in the tracker program, either misquantifying lengths or positioning. So the entirety of this experiment was used to quantify the amount of velocity lost in terms of the coefficient of restitution and to understand what that meant experimentally as well as conceptually. Thank you.